What killed the dinosaurs? Their sudden disappearance 65 million years ago, along with at least 50% of all species then living on Earth, is known as the KT event, Cretaceous Tertiary Mass Extinction event. Many geologists and paleontologists now think that a large asteroid or comet impacting the Earth must have caused a global catastrophe that led to this extensive loss of life. The Chicxulub crater in the Yucatan region of Mexico is a good candidate for the ancient point of impact. The crater is the right age, 65 million years old, and it is consistent with the impact of a 6 to 12 mile wide asteroid. The asteroid would have to have been at least that large to cause global disruptions. But how could one asteroid kill off over half of the species on Earth? Many scientists originally thought that the heat and dust of the asteroid impact could have caused the KT extinction. The scalding heat of the impact would have killed off life locally, and then dust kicked up into the atmosphere would have caused the skies to darken worldwide, halting photosynthesis and causing temperatures to drop. Animals that normally fed on plant life would have soon died of starvation. The predators, lacking their traditional prey, would have hunted each other until eventually dying out as well. But according to Buck Sharpton, planetary geologist with the University of Alaska, Fairbanks, and NAI member, this nuclear winter caused by dust theory can't fully explain the KT extinction. Dust itself is fairly benign, says Sharpton. We always have dust being sent into the air today, for example, because of volcanic activity. While dust may have initially contributed to changes in the climate at the moment of impact, dust rarely causes fundamental climate changes because it rains out over a few weeks or years. Hey everyone, want to be part of the Cool Science Club? Become a member and get early access to videos and a sweet badge to flex with. Just $1.99 a month, less than a latte. Join the fam now. Tab link in bio. Now come back to the topic. Sharpton instead believes that long-term global climate changes were caused by the vaporization of carbonate and sulfate rocks. The increased amounts of sulfur and carbon in the atmosphere would have caused long-term changes in the Earth's atmospheric chemistry. These changes, he says, lasted for hundreds of years and probably led to the extinction of many animal species. The Chicxulub region is especially rich in gypsum and other sulfur-containing materials. After the impact, both dust and the vaporized sulfur smog would have darkened the atmosphere and blocked sunlight. According to Sharpton, the dust would have rained out after the first few weeks or years, while the sulfur would have lasted from several decades to a century. With such a long-lasting sulfur smog, temperatures would have remained cool worldwide, and photosynthesis would have been suspended for several lifetimes. Sulfur was not the only vaporized element that affected the atmosphere. The impact at Chicxulub also vaporized carbonate rocks, releasing a lot of carbon dioxide, CO2, into the atmosphere. Sharpton says that while the sulfur would have been the dominant gas initially, after a century or so, the sulfur would have rained out of the atmosphere. Then the CO2 would have been dominant, as it can remain in the atmosphere for 1,000 years without dissipating. CO2 is a greenhouse gas, so temperatures, which had experienced a period of cooling because of the sulfur, would have immediately started to rise. This is the most detrimental swing you can imagine for organisms trying to cope, says Sharpton. Just as they begin to get comfortable with colder temperatures, you go and raise the heat on them. Sharpton says that temperatures probably only varied by about 10 degrees, but even such a subtle shift can have dramatic effects. A 10-degree variation, for instance, can substantially change how much of the world's water is locked up in glaciers. However, Kevin Pope, a geologist and archaeologist with GeoEcoArc Research, doesn't think the vaporized CO2 would have greatly affected the atmosphere. The amount of vaporized CO2 was not all that significant, says Pope. It would have, at most, doubled the amount of CO2 in the atmosphere. That's the same sort of increase that's occurred lately from the Industrial Revolution. And there's a lot of controversy as to whether this current increase in CO2 really has any effect. In Pope's view, the immediate short-term effects of smoke and atmospheric sulfur were the main culprits in causing extinction. Worldwide fires triggered by superhot ejecta raining down after the Chicxulub impact would have generated smoke, and the combination of smoke and vaporized sulfur would have briefly darkened the skies. Pope says this would have shut down photosynthesis for 6 months at the most. And while Sharpton says the atmospheric sulfur would have lasted up to a century, Pope thinks it probably rained out much sooner. According to our models, the sulfur would have only had significant effects for a maximum of 10 years, but some have suggested it could even be less, says Pope. Once the sulfur rained out after a decade, the light levels and temperatures would have rebounded. Although Pope says the smoke and sulfur would not have lasted long, he thinks they could have triggered significant long-term global changes. You shut down photosynthesis for just 1 year and the ecosystem collapses, says Pope. 99.9% of all life on the Earth is dependent on the sun. Take out the sun and you knock out the first tier of life. The brief cold spell could have pushed the Earth into a new regime, altering the atmosphere and the ocean circulation, leading to changes in the carbon cycle that lasted hundreds to millions of years. Sharpton does not agree with Pope's assertion that short-term darkness could have caused global extinctions, however. As those of us who live in the Arctic know, plants and animals can tolerate several months of darkness quite easily, says Sharpton. Paleobotanical studies of the Canadian high Arctic, for example, show that during the early Tertiary, stands of maple trees, crocodiles, and other temperate and even tropical species existed. These times were warm, but they were characterized nonetheless by extended periods of darkness where photosynthesis was not possible. Whatever global climate changes occurred, more than just the dinosaurs were affected. Almost all large land vertebrates and tropical invertebrates were wiped out. Many water-dwelling organisms died as well. Acid rains, created by the mixing of vaporized sulfur and water, acidified lakes and streams. According to Sharpton, the acid rains also acidified the top layers of the oceans, especially near the impact site. This killed off the plankton-like microscopic foraminifera, which lived in the top ocean layers. The calcium carbonate-shelled microorganisms were in trouble when it began to rain sulfuric acid, because acid dissolves limestone, says Sharpton. Those organisms found themselves in a world of hurt. Pope disagrees with this assessment, however, and says the acid rains could not have acidified the top layers of the oceans. There definitely was acid rain, says Pope, and clearly a lot of microorganisms were hit hard. The acid rains would have acidified the lakes and streams, and it would have also acidified the soil, affecting plant life. But there just wasn't enough acid to acidify the top layers of the oceans. They're too vast. Pope instead thinks the foraminifera were harmed by the decrease in sunlight when smoke and sulfur darkened the sky. Darkness either directly caused the organisms to shut down, or it affected the photosynthesizing plankton that they ate, says Pope. These organisms lived in the top 30 to 100 meters of the ocean, where sunlight can pass through. There is no energy reserve. When you shut off the sunlight, they just die, and everything dependent on them dies. It's not like the mammals that were able to scavenge on the dead and thereby survive. But Sharpton argues that planktonic life forms merely become inactive during periods of darkness. The Arctic and Bering Sea, as well as much of the Southern Ocean, are continuously dark 6 months every year, and yet plankton abound, says Sharpton. Regardless of how they died, many scientists now look to foraminifera rather than dinosaurs and other land animals to record the rate of extinction at the KT boundary. Dinosaur fossils are very rare, explains Pope. Of all the dinosaurs that were once on the planet, we have only found a fraction of a percent. Because they're so rare, tracing the dinosaur fossil record is hard. A better fossil record to trace is the marine microfossils. They are very diverse, evolve quickly, were super abundant, and so much easier to track. They show a clearer story of extinction at the KT boundary. Sharpton says that although the Chicxulub impact seems to be the logical cause of the KT extinction, there's still a lot we don't know. In fact, he says we may never know the exact cause of extinction. We have good circumstantial evidence, says Sharpton. In a general sense, we have it nailed down, the case is closed. But as to the particular cause of the extinction, be it dust, sulfur, CO2, or smoke, we don't know. When you roll all those things up together, it's a wonder that anything on the planet survived. It makes me think sometimes that we're all out to lunch, that there's something critical that we're overlooking. It's possible, he suggests. The impact could have affected just a few key organisms that were somehow interconnected with many other species. It's like the stack of cans at the grocery store. Remove a few of the top cans and the structure remains sound, but take out a bottom can, a load-bearing can, and the whole thing will come tumbling down, says Sharpton. It could be that the interconnection between organisms is so absolute and yet so subtle that removing only a few organisms would cause the whole biosphere to collapse. Studying impact events like the Chicxulub crater can help astrobiologists understand the close connection between life, geology, chemistry, and how such impacts may disrupt this relationship. Sharpton, for one, doesn't see such impacts as a completely destructive force. The Earth is such a complex and fragile structure, but it managed to withstand the Chicxulub event, says Sharpton. Life rebounded. These impacts destroy life, but they can also promote evolution. If it weren't for the Chicxulub impact, where would we be today?